Let's go on now to developing similar equations for the CSTR, the continuous stirred tank reactor, and develop the simulations, and let's view how that performs under steady and unsteady conditions. So of course the CSTR, we're constantly streaming in and streaming out here, and that entire reactor is perfectly mixed. So if we develop the equivalent equations here, let's retain the accumulation term for now, and we've got flow in, so flow in and flow out. And one of the conditions of a CSTR is that it's perfectly mixed everywhere, so the concentration is the same everywhere, so the temperature is the same everywhere, so the rate is going to be the same everywhere, so we can remove the rate as a constant of this integration and just rewrite this as RIV. And of course we can expand each of these terms in terms of concentration and flow rate and so on. We are going to specify further that we'll develop this for constant and equal flow rates, and of course we can generalize that later on. For now, let's just say the volumetric flow rates are fixed and constant, and let's just expand in terms of the reaction. So let's just use the same reaction here, so A to B with the rate constant of K with the rate expression of minus kCa. So we can write this in the first component, so we can write ddt CAV, and then Fi in is going to be the volumetric flow in multiplied with the concentration at the inlet point Ca in, and then the flow out will contain component A, which is at the same concentration as the concentration inside of the reactor. So by virtue of this perfect mixing, the concentration is the same at all points in that reactor, including the point immediately at the exit. So that's going to be a Ca as well. So we can say minus QCa here, and then Ra is going to be minus kCa, so minus kCaV, and then dividing through by V, taking V as a constant because Q is constant and equal for in and out. So we can rewrite this as dCa dt equals, and this will be Q over V into Ca in minus Ca, and here it's minus kCa, so we've divided through by the V. And of course we can introduce the definition for space-time. So space-time is V over Q, so this is 1 over tau into all this. And let's just group it in terms of Ca. So this is let's write it as Ca in over tau, and then minus Ca into 1 over tau plus K. Right, so that's dCa dt. And of course this is a fairly simple differential equation to solve, because we've got these terms all being constants. So because our flow rate is constant and the volume is constant, 1 over tau is going to be a constant. If it's isothermal operation, then that's also a constant, so that's all constant. The inlet concentration we are assuming to be constant, so we are constantly feeding this fixed concentration of A in here. So that's a constant. We've just said that's a constant, so this whole thing is constant. So this is an equation of the form dy dx equals k1 plus k2y. Right, so we can easily solve this equation analytically, but we're going to introduce now a numerical way of solving this equation, and that's because of the power of these numerical solvers. So we happen to have a very nice, easy equation in this case to simulate, but of course the equation could easily become more complicated than that. It could be simply that these kinetics are unrealistically simple, and if we substitute with other kinetics, that we'll get a more difficult equation to solve. It could be that the flow terms are not as steady as we've mentioned here. It could be that there are other things that are changing in time. Maybe the flow rates are changing with time and so on. So this equation could easily be more complicated, and numerical solvers are more convenient in that case. So we have this equation. It's a first order ODE, so we'll need an initial condition to solve this. So we'll just specify an initial state here that Ca at t equals 0 is simply defined as some initial concentration Ca0. Please note that the Ca0 is the initial concentration in the reactor. It's not the same as Ca in. So Ca in is the inlet concentration to the reactor, which generally speaking is different to the initial concentration in that reactor. So let's simulate this now in MATLAB. And to do that, we are going to use this ODE solver command. So let's just set this up first. So we're going to save this as SO2, our second simulation of the day. And we are doing all this in the public distribution folder, simulations. So I'm just copying this path across. So that's SO2.m. .m. Okay, and we're going to say here close or clear or CLC, so the usual initializer. Oops. And let's specify some numbers. So let's specify that the initial concentration in the reactor, let's say that's simply 0, that we didn't have any of component A in that reactor to begin with. Okay, then we need to specify Ca in. Let's just say that's 20, so 20 moles per cubic meter entering that reactor. And we need to specify the space-time of that reactor, V over Q. So let's let that be 1 hour. So 1 times 3,600. So we've got space-time, we need to specify K still, so K. Let's arbitrarily choose this as 3 times 10 to the minus 4, and that's going to have units of per second. And that's pretty much it. We are ready to simulate this equation. Now let's talk a little bit about what numerically integrating an equation means. So let's say we have some function. Let's say we've got dy dx is some function in x and y. And let's say we've got some initial condition. So let's say that's our initial point. So much like we've specified concentration at a specific time, we can specify an initial value for y given some value of x. So given this point, we can say that we at least have one value of our solution. So we know an x and y value in the solution. So we could simply stick those numbers into this function here, and that would specify to us a rate of change of y in x, or I should rather say a gradient of y in x. So we stick in x and y here, and that gives us dy dx. In other words, that's giving us the gradient of y with respect to x there. So what we could do then is simply step forward in x. So we can choose some delta x here, and we could say that look, if that's the gradient at that point, then after delta x units, I will be approximately at this point. So I could take just my my initial point and then add the gradient multiplied by delta x. So maybe I should write it like this. We can say delta y over delta x equals f at x and y, or rather it's approximately that. So delta y equals f delta x. So we've got f here, we've got the gradient here, and if we just multiply that gradient by delta x, that will give us a delta y, a corresponding delta y, and we can step up to that point. And that gives us a new approximate point, and we can then re-evaluate this gradient. So that gives us yet another estimate, and then we can step forward again, and so on. So by stepping forward, we can span out our solution. Now, of course, the way I've described it is quite approximate. It relies on us having a very good estimate of the gradient from just the one point. And there are much more sophisticated methods than this. So for instance, when you step to the next point, you could reevaluate the gradient there and try and work out, did I actually make a good estimate, or should I maybe average these two gradients and re-estimate that point, and so on. So there are lots of algorithms that help us do that. And of course, we could optimize the step size as well. So we'd like to get a solution quickly, but at the same time, we can see that if we make delta x too big, then our estimate for the next point is going to be more inaccurate. So there's some optimization to do in terms of the step size. There are cleverer things that we can do in terms of estimating the gradient between 2 points. So all those algorithms are things you'll encounter in the numerical methods course. So that's all fine. In this course, it's sufficient to understand it at this level, that a numerical solver works basically by looking at your current state, estimating the gradient, and then stepping forward. And that's pretty much how MATLAB's ODE solver works. So the ODE solver is basically, you can see at the heart of it, we need to estimate this gradient, right? We need this equation. So let's specify that first of all. Let's create a function, and let's create a separate function. So we are going to save this in a specific format. So I'm just going to save this in that path again, and let's call this SO2 diff. So this is where we're going to store the differential equation for the second simulation. And we're going to say here function, what is the syntax? I think it's dCdt equals, no, I think it's dCdt equals function SO2 diff t comma c. And I'm just going to save this. Oops, I think I didn't save it as a .m file. That's why I'm not getting my syntax highlighting. So .m. Okay, right. And, well, I'm pretty sure this needs to be like this. We'll see. So let's write dc dt equals, and let's, well, that's dca dt, so let's be a bit careful there. And say ca in over tau, so ca in over tau minus ca into 1 over tau plus k, 1 over tau plus k. Now, of course, ca doesn't actually exist at the moment. We've got this kind of abstract c over here. So c can be a vector, right? This we could have specified a vector here. So let's just say ca is going to be the first element of the vector, and we also need ca in and tau and so on. Now those are variables we've defined in the other file, in the SO2 file. So if we've specified them here, we won't necessarily have access to these variables when we are trying to run the differential equation. So what we're going to do now is globalize these variables. So we're going to say here global CA0, CA in, tau k. Oops. So these are all globals now, and I'm just going to copy that line and paste it in here. By the way, the shortcut is Control page up and page down to just switch between these two files. So you can see it highlighting here, SO2 and SO2 diff. I'm just switching Control page up and Control page down. So we've got this these variables globalized, and you can think of this as creating a pipeline between those two files. So you've created this pipeline between CA0 that will be created here and the CA0 that will exist within this function. So we'll have access to these variables now, and we've created a dCA dt. So what this function expects is a dC dt. So we'll return that. So we'll say dC dt equals dCA dt. So that's fine. It looks a little silly. I mean, why didn't I just make this a dCA dt? Well, obviously it's going to be because later on I'm going to want to introduce component b as well. So in that case, this variable c will be a vector of a and b. So in that case, I would use cb equals c2, and dc dt I would create as a vector like so. Oops. dcb dt, in which case we'd need dcb dt. But anyway, let's not get ahead of ourselves. Let's comment that out for now. So we are just solving component A for now. Right, so that's a differential equation. So at the moment, if we run this main file, this SO2 file, you can see all that's going to happen is these variables will get declared, and nothing else is going to happen there. So we need to create the instruction for MATLAB to go ahead and start integrating this differential equation. So we will use the ODE suite of solvers. So to do that, we'll say here t comma c, those are the expected output variables, equals ODE 45. And you see there are many ODE solvers in MATLAB, so we'll just use ODE 45. And you'll see in your numerical methods course, these are steps, those have to do with how many steps you are using in your integration and so on. So anyway, ODE 45, and we need to specify the name of the file in which the differential equation is stored. So we need to say here SO2 diff. Right, so when MATLAB is trying to run this ODE, it's going to look for this file, and it's going to use that file to evaluate the gradient. So we need to specify a few more things. We need to specify over what time period we want to integrate this equation. So when we said here that we are going to integrate and look at the solution, we have to specify, well, we want to know from this initial value until some time in the future, that's when we want the solution. So we'll specify arbitrarily here. Let's start at 0 and let's go for, say, 2 hours. So 2 times 3600. Right, so that's the range over which we are integrating, and then we have to specify an initial condition. So we'll say CAO to specify the initial value, and that's pretty much it. So what will happen is ODE 45 is a method in MATLAB which is then going to continuously try different estimates. It's going to call on this SO2 diff file many times. So as we said before, the first step in doing the integration is to estimate for the first point what the gradient might be. So MATLAB will stick in the initial values. So what it will do is look in this range, and it will use the first value of this range as the initial t value, and it will use CA naught as the initial C value. So those will come in here. So we'll have T and C defined, and then that defines CA, and you can see we need CA over here. The other things are constants, which we have defined in the other file. So that's all enough to evaluate dCA dt, and then that gives us dC dt, which is what this function returns over here. So let's see if that works. Let's go, oops, MatLab's closed. And I'll need the path. So remember, CD to change directory there. Use quote marks if there might be spaces in your path. So we're there now, and we can run SO2. Oops, so there's some error here. Yeah, so here we forgot to use a minus sign on line 8 of SO2 diff. So that's how you find your errors. So we need a multiplier here. Okay, so that's run. So we have a solution now, but of course we haven't told MATLAB to do anything with that solution. So let's just plot it out. So we can say plot t comma c, and let's label some axes. X label time t, and y label concentration C, and that's moles per cubic meter. And let's label that particular curve component A. Right. Okay, so we can see here we've specified the initial concentration in the reactor to be 0, so that's where it started. And as time goes on, the concentration rises. So that's because we are constantly feeding component A to that reactor. And it's rising. We are feeding at a concentration of 20 moles per cubic meter. So if we switch back to our drawing, we've started with a concentration of 0. We are feeding at a concentration of 20 moles per cubic meter. But as we are feeding component A, A is also being consumed by that reaction. So before this reactor can build up all the way to 20 moles per cubic meter, it gets consumed, and it seems to be stabilizing already. So let's increase the time range here and see if we've settled down to some specific number. So let's extend the time range to 5 hours. So after 5 hours of operation, what's the system look like? And you can see here we seem to have steadied out. So we've reached a steady state in this reactor. Now, we could, of course, check that that steady state makes sense to us. So what we should do is go back to this equation and ask, what's the steady state solution? So steady state, of course, will be when dCA dt equals 0. So if the left-hand side here equals 0, then clearly CA is going to equal CA in over tau. So just writing this part of the equation, and then taking all this across and dividing through by this. It's divided by 1 over tau plus k. In fact, we'll get a neater equation if we multiply top and bottom by tau, but anyway, let's leave it like this for now. So this is the steady state version of CA. So let's see what number we get for this. So CA in over tau, so we can say here CA steady state version is CA in over tau, so CA in over tau, and then that divided by 1 over tau plus k, 1 over tau plus k. And let's run that. Okay, so of course it's redone the whole ODE solution, and the calculation that we've done down here has returned a number for us. So that's 9,61, 9,62, let's say. And you can see this looks to be about right. That looks to be the steady state that the system does settle down to. And of course we can zoom in there and confirm that number. So let's do that. And you can see it's about 9,62. We can zoom in a little bit more. Yeah. So right, it's pretty close to the value that's been found here. So we can say that's consistent then, that the steady state prediction of the concentration in this reactor is the same as the steady state value that we observe when solving this this ODE without making an assumption.